Welcome. This lecture is called Linear Combinations. We are going to discuss arrays, really operations that have a specific shape. In particular, we're going to make use of two of the main operations on vectors. We had previously mentioned that there is an operation that looks like this. This is what we call scalar multiplication. So now imagine that we have a scenario in which this type of operation is repeated for multiple column vectors. So that is a scalar in front of each of those column vectors is being multiplied, and then we are adding them up, right? So a scalar column vector multiplication gives a vector, a scalar multiplied by a column is a column, scalar multiplied by the column is a column, and adding these four columns is going to lead to having a column itself. So all these columns are supposed to be of the same length. This is just one way of visualizing some of the operations on vectors, which involve scalar multiplication and addition of vectors. If we would like to use certainly sophisticated notation, then we would denote the scalars with the letter alpha here. So all these numbers are the so-called scalars. Okay, they're the so-called scalars that assume to be complex numbers, and each of them appears as a coefficient multiplying the column vectors. So this expression is the analogous expression for n, an addition of n terms, each of those terms being a scalar multiplication, and the addition of these scalar multiplications is what is called a linear combination. That addition, this sum, is itself a column vector. So here we have an illustration with four column vectors and four scalars, and so the idea would be that we are going to multiply each of these vectors correspondingly by each of these values. We're going to do the scalar multiplication operation. So we start with alpha 1 times u1 plus alpha 2 times u2 plus alpha 3 times u3 plus alpha 4 times u4. So that's going to look in this way. And when we carry out the first scalar multiplication, we're going to end up multiplying every value in that column vector by the value of that scalar. So the first operation looks like this. On the next operation, we're going to multiply every value by -4. So this sort of what's going on here is a little bit of distributivity. You can think of that scalar distributing in the scalar multiplication sense across each single location of that column that leads to this vector, and we do the same for the next scalar, and that yields this vector, and the last one gives us this vector. So at this stage we have the addition of four vectors, right? So what we do is that we go to every location. Location 1, for example, involves adding 2 plus minus 24, that would be minus 22, plus minus 10, that would be minus 32, and plus -3, that would give us minus 35, and so on. So every location is going to resolve by adding those numbers in that particular location. That's how we arrive at this vector here, which is the vector this linear combination is equal to. So at the end of the day, the linear combination equals to a vector, and you can think of that linear combination equated to that vector as being a vector equation. And on that note, we are going to recall one of the main goals of the initial goals and the initial topics in this class, which is something that has to do with systems of linear equations, right? So if we group the linear equations here into a vector, this is an example with 3 equations and 3 variables. We can group those equations into a vector, and that is equal to another vector. what we're going to do now is, remember how we would write the matrix of coefficients and then the augmented matrix? So we're going to take a look now at the variables x1 and specifically at the coefficients that are multiplying those variables. We're going to do that because we're going to write those variables with x1 line up here in a column vector, and we're going to notice that each of those, so here's a 1 multiplying x1, and we're going to notice that we can think of this as a x1 as a common factor, if you will, and we can write this vector is exactly equal to that vector. So this is like doing scalar column vector multiplication in reverse order, and so we're writing this column vector in terms of a scalar multiplication where the scalar is x1 multiplying that column vector. So we can do the same also for the column vector that collects the terms with x2. We observe that the equation, the third equation here, has a term 0 x2, right? And so the coefficient multiplying x2 is 0 on the last location, the last entry of this column vector. And then we can write this whole vector, we can write that as scalar multiplication, x2 multiplying that column. And similarly for the terms with x3, right? So we can see those terms appearing here on the initial set of equations. They are collected into this vector, and then from that vector we can write that vector as a scalar multiplication. So the important thing is the vector of constants is kept on the right side of the equation, right? We keep writing this vector of constants everywhere. So this would be another way of interpreting, another way of writing the linear system of equations, but making use of the new definition of linear combinations. In other words, the system of linear equations is a linear combination which initially the values of x1, x2, and x3 are unknown, but by means of doing the row reduction, transforming, forming the augmented matrix and row reducing, then we can determine what is the solution set. And so in this case, it is found by means of those type of calculations that this system of linear equations has a unique solution, and the values of the solution are -3, 5, and 2. And that means that if those values are plugged in, right, if we write -3 as a coefficient, as a scalar in that scalar multiplication, and something similar for the last x2, we write 5 for the second scalar, and then we write 2 on the location of the third scalar. So this would look in this way. And so the important thing now is to verify that this expression here on the left indeed becomes the vector we have on the right side. Right? That type of verification is not very difficult to do, but we can you can outline here the steps, kind of operation that we've been doing. So we would like to verify what is this equal to, and so we could do this here: 21 minus 15 minus 3. This would be -30, 25, 0, and this would be -24, 14, and 8. So it's not too complicated to verify that 21 minus 30 minus 24 is equal to -33, minus 15 plus 25 plus 14 gives 24, and the last one, -3 plus 8 gives 5. So that's a verification, and